We are basically providing energy efficient solutions to the electric vehicle companies, and not just electric vehicle companies, to the renewables. Wherever you need a reliable solution of energy storage, we are open to provide. Now, before I begin my presentation, we're going to talk about electric vehicles. As we all know, the reasons behind why we should switch and move towards e-mobility and sustainable energy and renewable energy. The global issues such as pollution, air pollution is one of the factor. Climate change, global warming. These are some factors that are really critical. And of course, these days, coronavirus is critical. But I just hope it will pass away with time soon, and it's temporary. Coronavirus, this situation has taught us some really good things. One of the things which I feel when I go outside and when I breathe outside air, I can feel the freshness in the air. I stay in Mumbai, and I can actually I can feel the difference when we in a regular life, and now it's so pure. And I wonder why we not choose to stay in such kind of environment. And do we really intend to keep our our children's and grandchildren's to grow up in such a bad atmosphere, bad environment, and breathe in such a unpure air? I think this is high time we should think about what we should take responsibilities of what we are doing to the nature, and think about doing the right things. Electric vehicle is one of the major factors. So guys, so I think electric vehicle, we all know a basic about electric vehicles. It is not something that has developed yesterday or day before yesterday. It has been developed parallelly with IC engine. It's been more than 200 years. So I'm gonna take you back in the history and share the evolution of the electric vehicles from the beginning and the eras of mainly the electric vehicles. So these are the first inceptions. There were some entrepreneurs and engineers from UK, Robert Anderson, in the US, William Morrison, and they actually proved the concept of electric vehicles on lead acid batteries in 1850s. And during 1900, one of the third of population of US was actually using electric vehicles. So it is not something which has developed yesterday or day before yesterday. These are some automobiles that has been developed. The first electric carriage was built in 1830s, and in the US, the first electric automobile was made in 1891. In 1908, if you can see the top right image, Henry Ford introduced Model T, which is a very well-known electric vehicle. And then, if you can see just below, in 1974, Vanguard, it looks like a toy car to me. It's a two-seater electric vehicle, and it reminds me of Reva. If you can connect Reva to this, I have seen Reva in my childhood. Reva used to work on lead-acid bulky batteries. The performance was really not that appreciated at that time. So it was just for local commute, people used to use it. Then in 1988, General Motors, if you can see the bottom image, they have come up with the EV1 model, and it became very, very famous in the US and global platform. In the US, from 97 to 2000, a few of thousand EVs were available on lease. So that was one of the era where the IC engine was not that developed, but electric vehicles were used. Okay, so in the year 2003, General Motors discontinued the EV1 model, and actually they killed the entire electric vehicle program. They actually literally they killed it. They are known to kill the whole evolution of electric vehicles. But at the same year, it motivates the two engineers and entrepreneurs to come up with a better solution, because because General Motors wanted to promote their IC engine, their diesel engine, and their IC based cars. That's why they try to put it away, and they try to deviate the force towards the IC engine. At the same year, in 2003, two engineers named Mark and Martin, they come up with the solution, or they come up with a concept, and they formed a company named Tesla, very well known these days. And it took them 4 years to come up with a first model, which is Tesla Roadster. They proved the concept that it is a high-speed sports car. It can give you the performance of a sports car. So there were obviously the bottlenecks. The bottleneck of the electric vehicle was the battery, and obviously the powertrain. So they tried to solve all those issues. And in 2007, they've come up with Roadster. It was a big news. Roadster was just a proof of concept, and it was for the elite market and for all the sports car lovers. And I think in 2004, they raised the funding. Elon Musk was the investor by VC funding, and he became the chairman of the board in 2004. He, I think, invested $7 million in the startup. Meanwhile, in China, in 2008, BYD is a plug-in hybrid, and it's very, very, very big name in China, and also in Europe. BYD launched a few of the compact sedans, and these numbers, if you can see, in 2009, they were able to sell 440,000 vehicles. That was pretty good number at that time. But these all were hybrids, plug-in hybrids, and this number got double by 2016. Also, Nissan launched a series of electric and plug-in hybrids. If you can see in the last image, they made a mark by selling 1 lakh units by January 2014, representing 45% of electric market share in the whole world. But Nissan is pure electric. Sorry, this one is pure electric. This is hybrid. So let's not just confused in pure electric and hybrid. If you have any questions, you can ask. By the end of next year, maybe in 2 years, they were able to sell double capacity to 2 lakh capacities, which was the milestone they have reached. That was pretty impressive. So yeah, okay. So this is one of the favorite companies you have, Roadster. They made Roadster first, then they come up with the Model X, then Model S, then Model 3. Nowadays, they're making news for Model 3. Roadster was, as I said, it was for elite market. The first version was somewhere in the range of 120,000 US dollars. Now the second version, which is more powerful and it has better performance, it is coming up somewhere around 2 lakh US dollars. Whereas Model S, they launched after couple of years. It is somewhere around 80,000, but they have the US subsidies of 10,000, so you can buy it at 70,000 US dollars. So these prices are getting down, not because obviously because of the mass productions, but also the degradation, also the reduction of batteries. Because in an electric vehicle, half of the price is battery, 50%, more than 50% is the battery. So the cost of the batteries, they were able to reduce by producing the batteries by themselves. Earlier, they used to take the batteries from Panasonic during the phase of Roadster, but soon when they really wanted to commercialize the product and getting into the mass manufacturing, they had a joint venture of Gigafactory with Panasonic in Nevada. And now they own 4 gigafactories. So they are producing the cells, they're producing the batteries and the bulk. This is a specialty of Tesla. They make everything in-house. They have the psychology to make everything in-house to control the cost and the quality, including the casting and everything, including the induction motors also. So as I said, Model 3 was meant to target the most commercial market, bulk market, and people like middle class people can afford these kind of vehicles. Roadster is a sports car, very expensive, but I think if you compare the performance of this car, I think it's very, very, very cheap. I will explain it to you in the next slide. There are some good news. Last month in March, Tesla produced 1 millionth of all electric vehicles, which is a good milestone. Out of 1 million, out of 10 lakh, 50,000 units were delivered only Model 3. Now you can imagine at what level they are producing Model 3 and at what cost they are producing Model 3. So making Model 3 as all-time best-selling EV in the world. So if you can see here, you have two sports car, Bugatti Chiron and Tesla Roadster. Bugatti Chiron, always known for the one of the fastest sports car in the world. Obviously, it has the another version, another variant which can go up to 300 miles per hour. But I've taken a example to compare the performance. So if you take Bugatti takes 2.4 seconds to go 0 to 60 miles per hour, 0 to 100 kilometers per hour, whereas Tesla Roadster takes just 1.9 seconds. So if you see, it is able to beat the performance. It is much faster. The acceleration is much better. The top speed is almost the same. The difference is just 11 miles per hour, and then there's a miles. Even in a single charge, it can go up to 620 miles, whereas it's a IC engine, so there is no sense of comparing. But if you compare the cost, the Roadster it's costing 2 lakh US dollars, whereas Bugatti is costing 30 lakhs. It's almost 15 times. So if you have the money, I would say you will go for Tesla Roadster. You can enjoy the ride. And for me, for everyone actually, top speed doesn't matter. What it matters is acceleration, and it has the better acceleration. So they were able to prove the concept that electric vehicles are much more efficient than IC engine, because the losses are less, and it depends on many factors. Not all electric vehicles can give you the same performance. Obviously, Chiron is not the fastest in the world, not even neither Roadster. So I think Roadster comes on rank 8th. Fastest EV, which is this one is the fastest. Neo EP9 launched last year. It can go up to 260 miles per hour. It has some records. It has some records in Germany in some of the tracks. It can beat many cars. So it is the fastest among us. And interestingly, it is Chinese. Neo, the headquarters is in China. It's a Chinese company. So coming up, Rimac C is the second. It takes the second place. It can go up to 258 miles per hour. Acceleration 0 to 60, 1.85 seconds. Range is okay. The most interesting part about it, if you can see, the battery capacity is 120 kilowatt, whereas the peak power, it can go up to 1400 kilowatt. If you do the math, it is 10 times, more than 10 times. That means their cells are able to deliver 10C rates as per their capacity. They have the most powerful cells which are being used. So the performance, the acceleration, everything matters on the battery itself. You cannot achieve these kind of discharge on lead acid or any other batteries. You have to make sure that you choose the right batteries. Okay. Next is number 3 is Pininfarina Battista. Pininfarina is the name of an Italian designer. He's one of the best designers among the world, just like Ferrari used to be. And it makes very good-looking and beautiful cars. This car owns number 8. So wow. I think Mahindra owns it. Mahindra has brought it a couple of years back, and they have launched this product on a global platform. They're not going to consider it launching it here. Don't worry. So talking about Mahindra, Tata is no longer away. So this is one of the aviation concept car they have made for Indian market. This is one of the. I mean, I would say it's for the mass market. You can see the interiors so beautiful and sexier. I would say the price won't be more than 15 lakh of this vehicle. Performance side, it will be the competitor of maybe Ciaz, Suzuki Ciaz or something. But if you see the looks, I think it's killing it. And I think it will take time because it's just a concept and prototype level. I think it will take a couple of more years to come up at the production level. So Tata is no far. Okay. Interestingly, upcoming EVs and startups. These are some. Rivian is one of them at the global platform. All three are based in US. These are some parameters performance-wise. These are good performance and fast vehicles. Faraday Future is one of them. Lucid is one of them. This one is Lucid, this is Faraday, and this is Rivian. I've heard Rivian is facing some challenges due to the lockdown situation, so they're gonna extend or postpone this program for a couple of more years. But that's okay because it was just an R&D program and not for the mass bulk. They are the rivals of Tesla truck. Okay, one of a different example is Creasel Electric. It's a startup company. Their business model is a little different. They don't have their own vehicle. What they do, they select some vehicles and they convert it into electric, and they convert it without compromising of any performance. They were able to do it, and their business model says their states they're going to do the prototyping. They're going to convert it, all the retrofitting, and they're going to provide you the car manufacturer. They're going to provide and make the batteries, and similar to what we are doing in India. Coincidentally, and not coincidentally, we had a history with them, with Crystal Electric. They are based in Austria, upper part of Austria, in a town named Freistadt. We have a good history with them. We were in association with them to cater India market. We have started some projects from Tata, but because of the costings, I have already visited them. During that time, they used to work. 3 years back, I visited them. During that time, they used to work in containers and in a garage. So if you go through their website, you can find a lot of good things. Not just Porsche, Panamera, they have done with Hummer, they have done with Mercedes G-Star, many cars. So they have already got business, and they are now they are finished up with their factory, and they are producing at a bulk level. I think 600,000 megawatt hour per year, which is good capacity. Because the costing, India seems to be a very price sensitive market. The costings didn't suit. That's why we had to terminate our association with them. We have done a lot of marketing work for Creasel. If you see at our website, our older website, you can find Creasel products. We have done a lot of marketing and exhibition participation for them. But the costings are very high. So I think at that level, at that costings, we won't be able to sell anything because the quality is very high. European quality always high. So I've done a small calculations to understand the commercial model and to make the comparison commercially, so that we all can see that it is commercially feasible to buy electric vehicles. So I've taken an example of Mahindra e-Verito. The price of the vehicle is it's full electric. It has the battery capacity of 18 kilowatt hour, range 140 kilometers, price 10.5 lakhs. So if you charge the vehicle at your home, the price will be 4.75 per unit, and the cost of the 140 kilometer will be 88. And I've done the comparison with the Honda Amaze. These are the prices. These are the petrol and liters. So the cost for the similar range for 40 kilometers is coming up somewhere around 683. So if you do the payback analysis, the difference in the price is just 1 lakh, and this is the payback comes to be 2 years, which is pretty good. And after 2 years, what you are going to do is you're going to save all the money from your operational cost, because running per kilometer or on an electric vehicle is somewhere around 0.5 rupees, whereas in here it's somewhere around 4.5 or 5 rupees. So it's almost 10 times extra. Okay, let's talk about the battery technologies. Right now, commercially available battery technology is lithium ion with the NMC, LFP, and LTO. Each and every technology has their own advantages. Before I explain you this, let's take the criteria of the battery chemistry selection. When we select the application, we have to go through the selection protocol. The criteria for battery chemistry, first is the energy density. Energy density is the amount of energy you can store per kilo. It plays a important role because weight matters a lot in an EV. Second is the volumetric density. Comparing with lead acid takes somewhere around 5 to 6 times extra space as compared to lithium ion. Then is the power density, which I just explained in Rimac C concept. The battery was able to deliver more than 10x power for the requirement for the peaks. That peaks could be 5 to 6 seconds, but it was able to do it. And that was the power density we are talking about. If you need a performance out of battery, you need to select the right chemistry and right battery. At the same time is the charging rate. It has to be fast charging. There are chemistries such as LTO, if you can see here. LTO chemistries can be charged fully from 0 to 100% in just 15 minutes. Yes, and then but it doesn't have all these criteria. It cannot fulfill all these criteria. So None of these batteries are able to fulfill all these criteria. So with the industry is going to come up with some kind of solution. Everybody is working global at the global level. Everybody is working to achieve all these criteria. Third is the cost. Obviously, it matters because, as I explained, to make a breakthrough comparison and to make a breakthrough to complete with IC engine, the price of batteries at the pack level, at the battery pack level, should be $100 per kilowatt hour. Fortunately, because of the mass production, Tesla has recently reached to close to 100 kilowatt hour per level. That means at the cell level, they are able to reach at $60 per kilowatt hour. So cost is going to be a criteria. Tesla is doing so many gigawatt hour at the very large level. That's why they're able to control the quality and they're able to control the cost. Currently, we are nowhere. Let's not get into this. So costing, it matters. I mean, if you really want to make a competitive product or make it a commercially viable, it has to be at $100 per kilowatt hour. So that recently they have reached, and along with Tesla, I think CATL has also reached $200. That means it's a good way to go. If you are manufacturing at a bulk level, this is going to be a big thing, and we would be able to convert all these IC engine based mobilities to e-mobilities. And yes, the safety. For example, here in the second lithium ion NMC, LFP, and LTO chemistries, we typically they use a liquid electrolyte which is ionic. In case of any heat generation, it has a temperature, it has a thermal runaway. If it exceeds to certain temperature, for example 70 degrees, it can explode. And there are many cases that there are many accidents and incidents have happened with Tesla also. So solid state batteries are one of the upcoming things where the electrolyte, just the electrolyte is solid state and it's not ionic at all. So the temperature is not going to be issue, but it has some other challenges. For example, it has the challenges of the mobility of the lithium ion. So the power density and charging rates are compromised with solid state batteries, but there is improvement going on. And with time, I think in the next 3 to 4 years, we will be able to see more development with solid state batteries. I think sodium ion does not have any potential, but people are using in some of the projects. Lithium sulfur seems to be one of the upcoming chemistries. Sulfur, especially in terms of energy density and cost. Sulfur can give you somewhere around 500 watt hour per kg, whereas NMC, which is commercially available at this time, can give you 300. So it is 50% and 60% more energy density. That means within a particular space and weight, you are able to store more and more energy. Then there is aluminium air. Some of the startups, even in India, Log9, Mumbai-based startup is working on this. They have a prototype ready. They have launched their product, but I think at global level and production level, it's difficult to manufacture aluminium alloy, so it's going to take time, and it has some other challenges. Aluminium alloy has a specialty that you don't have to charge the batteries. You just have to change the aluminium plate after every 1,000 kilometers. It looks good. But just imagine if you have to go, for example, you have a running capacity of 100 kilometers a day. Then every 10 days you have to go to the service center and change your aluminum plate. So it has the drawbacks. Then silicon and graphene based anodes are next upcoming things, which will be combined with these chemistries, NMC. Silicon has the other advantages. It can typically we use graphite, and people and at global level, I have a strong reason that Tesla recently have announced they have a 1 million kilometer cells they've recently launched, and which is also cobalt free. Cobalt is one of the metal that goes in the cell. If you can see, NMC sees the cobalt, which is very expensive and which is very rare to found in on Earth. That's why it's expensive. So it's cobalt free and it has silica. I think it has somewhere around 15% of silica, but they are also testing at 50%. They are able to reach at 50%. And with the same chemistry, they are able to reach at 4C charging. So with time, we'll get to know more. Next. Okay, this is the typical mechanism of how the lithium ion chemistry works. This is a positive cathode. Okay, so
Yeah.
I'll just try to explain you the mechanism, how it works. So this is a positive cathode. This is the anode, negative. It is copper. It is made of aluminum. During the discharging, electrons moves when you connect it with the load. Electrons move on the outer circuit. Lithium ions move from anode to cathode, and it goes in here. This process of sitting here is known as the intercalation, and there is a separator in between. Lithium ion are able to pass the separator, and the separator is for the safety of the short circuit. Otherwise, it will be short circuit, and boom. If you see, these are the silica. These are the big molecules of the silica. Silica has the speciality. During the discharging, it goes back. Electrons moves back, and lithium ion travels back to the anode side, and they go and sit over there. This is a typical reaction. We don't have to get into this. Okay, so here typically we use graphite these days, and here is silica, which has the mAh per gram, the capacity to store energy, and typically means to capacity to extract more and more molecules of lithium is much higher than graphite. It's almost 10 times. But the reversible capacity of silica is much lesser. That means with the same amount of weight and same amount of size, if you're using silica, you can store 50% extra energy. If you are this is what Tesla has done earlier in their 18650 format. They were able to do at they were at 3 mAh capacity, and with their 21700 format, a bigger format, the volume was increased by 50%, but the capacity got doubled. Okay, so but silica has many challenges. For example, volume expansion during the intercalation process and lithiation process. There's an expansion of silica and there's a contraction. And during the extraction and expansion and contraction, there are cracks that developed on the SCI layer. That cracks basically degrades the life of a silica. But many companies on the global platform are able to solve this issue by using some additives which actually don't control the contraction and the expansion, but make sure that there is no cracks on the layer, on the SCI layer. So these are the challenges, and they have actually already sorted out. I think with a couple of years we are get to see more and more growth. Okay, so these are the typical operating range and the operating range of a lithium-ion batteries. Typically, this is a state of charge. For example, you see in your mobile phones, 100%, 90%, and typically they say to prolong the life cycle of the battery, you need to work on the range of 10 to 90, which is known as the 80% DOD. This is how we operate. And this is the voltage range 2 to 4.2. We actually cut it at 4.1 or maybe 4.15, and we don't go beyond 3. That actually depends on the chemistry to chemistry, different chemistries, different curves, different operational windows. So that's how we are able to increase the life cycle of the batteries. And we are able to do it by using the intelligence, which is known as the battery management system. Maybe in the next slide. These are the thermal runaway conditions. For example, if there is anything, if you are going out of those windows, you are actually going towards the thermal runaway. If you are overcharging, if you are over discharging, if there is a crash, if there is a high current charging or a nail penetration, you are moving towards thermal runaway, and that is going to explode. The cell is going to explode. So you have to make sure that there's a temperature range. Typical temperature range is 25 to 45 degrees. And you have to make sure that the temperature of the battery pack should be in this range. There are a lot of otherwise it can explode or it can degrade the life cycle. Okay, so when you design a battery pack, there are some design considerations. The basic consideration, actually not the last one is the application. So first you select the application. For example, for EVs, where you need high peaks, you need to select different chemistries. Even with the different chemistries, there are different cells with different performance. So it's important to understand the criticality of the application. For example, for ESS projects where you need a 20 years or 15 years of life cycle, you select different chemistries. So based on the application, you select the chemistry and the cell format. Cell format basically plays an important role in placing the battery pack. Cell formats are typical cylindrical, I'll show you, and some prismatic and pouch. Then the second criteria is the battery pack configuration. For example, the voltages and the capacity is a typical way of doing it. You need to increase the capacity, just add cells in parallel, and then you add in series, you are adding up the voltages. And for a performance vehicle, for a sports car, they actually go up for higher voltages, and they don't want to limit themselves to 48 volts. They go up to 400 volts. Otherwise, otherwise the current consumption is going to be high, or the core and the losses will be higher. Third is the structure. Third is the structure, electrical performance, and mechanical and thermal management. Structure, for example, mechanical. For example, in an application like EVs, where the battery pack is going to experience a lot of vibrations and shocks, so that you have to make sure that the connections of the cells with the bus bar has to be done correctly, and there is enough strength to bear those vibrations. Secondly is the electrical protection at the cell level, at the module level. There has to be a fuses or some sort of protection if in case of any kind of failure. Then is the thermal management. As I already explained, you have to maintain the battery pack in certain temperatures. So you have to do the cooling or heating. If it goes below, if it goes negative, or let's say 10 degrees, then it's going to be a challenge. It's not safe. So you have to heat it up. We have some applications where we actually heat up the batteries. Okay, then is the protection. This criteria, basically the same, internal and external fusing at cell level, module level, and pack level. For the protection, you also need the brain. Battery is basically Dumbo. You need a battery management system. You need electronics, which can control the batteries, which can monitor the batteries, which can manage the cells. When you are connecting so many cells in series and parallel, there's a lot of disbalance. So you have to make sure that the voltages of each string in series remains at the same. So you need intelligence that can control the batteries, and it can protect. It can communicate with the external, for example, motor drivers, motor controllers, and the charger. It can calculate the amount of battery charge that is inside the battery, which is called as fuel gauging. And state of health is one of the critical criteria. For example, with time and with performance, the capacity of the capacity of the battery basically degrades with time. So that's what we said. For example, if a battery cell says it has 2000 cycles, that means after 2000 cycles, the capacity of the battery will be 80%. For example, if you have 100% right now at the day one and cycle day one, at the end of the life, at the end of 2000, it will be 80% only. That is called the state of health, and state of health needs to be programmed with the SoC, so that you are operating everything in the window. So some really good algorithms and really good brain needs to be developed on the firmware to control the battery management system. Application I've already explained. You also need to control the charging rates and the discharging rates for the safety of your batteries and the performance and the life, obviously. If you have a rated current or rated voltage or rated discharge rate, then it should not exceed. If it is exceeding, then you have to cut it down, or you have to basically communicate with the load and charger. This is a battery management system, BMS, with a 48 volt. I think you guys can understand, all the electronics people. This is the main IC which is actually controlling the battery pack. If you see, this is a 48 volt system battery pack. It's just a pictorial view. It's just a representation. The PCB is very small. The battery pack is very big. So each of the string is connected with this via the registers and other things, which is actually controlling this entire pack. This is the contactor. This is the fuse, and then this is the microcontroller, the brain, which is driving this. There are many companies who are providing this kind of solution. Basically, you have to design your whole layout on the PCB. This is architecture is from NXP, companies such as LTC, who have different design, who have different IC, monitoring IC, and TI is one of them, Texas Instrument. And this is the microcontroller. So basically, what what many companies are like, they allow the microcontroller, or you develop your own firmware to control your battery in whatever manner you want. You write the algorithms in the real time operating system to check and monitor everything at the same time, simultaneously, and not on the sequential basis. So, and there are few designs, they use the AFEs, analog front ends, which you don't need to make any kind of firmware, which can be easy to go and just a plug and play option. Texas Instrument, I think they provide this kind of solution. Battery pack manufacturing. So this is cells made by Tesla. These are the cylindrical cells, and then from the cylindrical cells, you connect these cells in the parallel, connecting positive to positive, and make the batteries. These are made by Tesla, taken photographs of Tesla, and you connect these modules like this. And these are our modules, by the way. This is one of the finest technique we have developed. Our principles are driven by the Austrian company named Griesel, as I already told you, and we are gonna continue doing these for the automobile market. Basically, 95% of the pack manufacturers in India, they do the welding and they do the pack manufacturing. They don't know what to do. They do the spot welding, and it's very ruthless way of connecting the bus bar to the battery tab. If you see here, the tab thickness is very thin.
Why don't we use supercapacitor, which we use in place of lithium ion batteries and this charger? Can we use supercapacitors?
So you mean supercapacitors?
Yeah.
Yeah. See, in few of the applications they use supercapacitor, but it has the drawbacks. Obviously, you can charge the supercapacitor, you can store the energies in a very faster way as compared to battery. But the drawback of supercapacitor is it cannot hold the energy for a longer time like you can hold it in the battery. So it has the drawbacks. So it is not the direct replacement of the batteries. There are companies who are working on using the similar kind of technology with the help of graphene to improve the charging rates. So it is between. So here is supercapacitors, here is battery, and they are able to find a way in between here. One or few startups in India are working on it. So, but supercapacitor cannot replace the batteries directly. I was just telling the criticality of welding. So basically, you do the welding on the top. People use the spot welding, which is very ruthless way, because there is high current and there's a lot of heat that develops on the top, and that heat that flows inside the cell because the thickness is some part of the heat that goes inside the cell, and it affects the electrode, and it eventually affects the performance and the life of the cell. So doing the spot welding is not a way. So it is one of the techniques which this is our IP, where the temperatures, the temperature on the top is not more than delta 3. For example, the ambient is 25, so we cannot go, the temperature won't go beyond 28 degrees. The pulses form, we do the welding. Okay, this is a typical module of Tesla Model S. This is one of the finest module you can find. If you see, these are many cells connected in parallel first and then in series. This capacity of this cell of this module is somewhere around 5.6 kilowatt hour. They've used 18650. This is Model S, not for Model 3. Model 3, they have done a different. They've taken a different route of connection the techniques. If you see, they have used a very unique technique over here for connecting the bus bar to the battery tab. I will explain it in my next few slides. Now just let me check. This is the battery management system. These are positive and negative terminals. It has the cooling system, which I'll explain you. These are the wires that are coming from the bus bar, controlling and going into the BMS. This BMS is working as a slave. All these modules will be connected in series, and there will be one master, and all these will be work as a slave. And they have, as I said, this module is acrylic. And just let's go. Okay, so here, if you see, this is the cooling channel they have used. So this is, I was saying, the cooling system, one of the finest cooling system. In the cylindrical form, the advantage is the cooling, because you get more of the surface area to cool, and the cooling becomes more efficient, whether compared to the prismatic or pouch formats. So here they pass the glycol and water mixture into the tubes, and these tubes are thin aluminum. Obviously, this is isolated electrically, but thermally conductive, and it takes away all the heat of the cell. This is one of the finest. Okay, this packs have been developed in our lab. These are our packs. We have used a similar kind of concept. We are good in reverse engineering. So if you see, these are the bonds. These bonds are used in electronics, and the advantage of these bonds is to act as a fuse in case of any kind of short circuit, or in case of any kind of, for example, if there is any excess load is coming, and if the fuse on the battery pack side is not able to cut down the current. So in any kind of case, if the load requirements are extra and current is flowing is excess, then it will fuse, it will act as a fuse, and it will burn off. It won't affect the entire battery pack, just one or two cases. So it is on the safety level. On the automobile, you need a safety. This is all acrylic for the insulation, and this is similar capacity, 5.6, 5.8, or maybe more, 5.8 kilowatt hour, 7S. So basically, what they do is they use the ultrasonic. This is not a welding, nothing, no heat generation, no nothing. They feed a bond, they feed a wire, and they use the ultrasonic energies to disturb the crystal of the bus bar and the tap, and make sure it's a physical bond is made. And this bond is strong enough to take, the strength of this bond is strong enough. It has a good strength to take all the vibrations and everything. And the most important thing is there's no heat involved in the process, and it can act as a fuse. Sorry. This is the Tesla battery pack modules connected all in series. If you can see, there are 16 or 18 maybe. And this is how we place the modules together to go up to 400 volts. This is after the packing. This has been taken from Tesla factory. Okay, now this is one of our, since we're talking about the packs, these are one of our offering for the two-wheeler market. This is how we are connecting. I have not mentioned the capacities. We have the flexibility to go from 1.5 to 1.7 up to 2 kilowatt hour. In one case, you can just take it. You can just swap it or do whatever you want to do and put it in the two-wheeler, mainly for the e-scooters, scooties, just like Okinawa or some others. Secondly, these are our offerings for the four-wheeler. Like I mentioned, depending on the chemistry, we have to sometimes, in these pack, there's no cooling involved. In these pack, there are heatings involved. There are heat fins around inside this. Sometimes we have to heat up the cells to get the maximum performance out of it. So these are some of our developments. This is for our off-grid and energy storage. This is for stationary applications. We can stack these to make a combined product for high voltage or maybe high capacities. You can just connect it into parallel and series. This is our offering with the PCS. You can just connect it with the solar, and these are the loads which typically don't we don't actually get enough. You cannot support these kind of loads with the lead acid batteries, but with our batteries, you can actually support these kind of loads, ACs and your washing machines or your refrigerators. Okay, last is the global charging infrastructure. We have the levels globally: level 1, level 2, level 3. Level 1 is very basic, and especially in case of Tesla, it's very basic. It takes 4 days to completely charge a Tesla at level 1. So basically, Tesla uses level 2 charging, where the voltages are 240 and 80 amperes is the current. And I think in 1 hour, it can get up to 50 miles of charging. And with the fast charging, this is the public as well as private charger. And this is known as the AC charger because the output is AC. It will go, the conversion of AC into DC will be on the vehicle itself. Vehicle has to have a onboard charger for that. So that you can just plug it into your 3-phase supply or 2-phase supply. In the level 3, we have up to 300 amperes it can go, and it can charge the Tesla for a range of 170 miles in 30 minutes. Then we also have a superchargers. I think that is a supercharger. itself. It gives you a DC output, and it can bypass the onboard charger. I'll explain you in the next slides. The maximum capacity of a level 3 charger, supercharger by Tesla or by any other companies are somewhere, I think, 200 kilowatt. Okay, so this is how we are going to charge on board. This is the AC output. This is AC till here. Then there is a conversion from AC to DC onboard charger. In a Tesla, we have, I think, 12 and 16 kilowatt charger on board because of the space, and of course, because of the space, the limitation is there. Whereas the battery capacity is somewhere around 85 to 100, 120 kilowatt hour. So this is a typical case of onboard charger, and these are just the levels. Okay, I've already explained. Okay, this is interesting. It is a DC fast supercharger where the output, the conversion of AC to DC has already been done, and you are getting the DC directly on the inlet of your vehicle. You are actually bypassing the onboard charger, and you are directly feeding it into the battery after passing from the protection circuit. So, because if you are going to pass this from here, it will just burn out the whole charger. This is a representation of level 1 and level 2. You have an onboard charger. You have a AC input. This is the vehicle part. Then you have a rectifier. Then your BM is going to control the CCCV profile for the batteries. There is a protection circuit and everything on board. And in here, just the BMS is just controlling the protection circuit, and you are just bypassing each and everything from here.
So
Yeah.
wireless charging also available. Do they use at present? At present?
Yeah, it is available. Obviously, Tesla has a proof of concept, but it is not efficient. The efficiency is very poor, and they have a wireless charger available, but the efficiency is very, very poor. And I don't think it has the potential to grow up. So wireless is available, swappable is available. So Tesla, a few years back, they have shown a proof of concept that there are a robotic arm that comes and it takes out the battery, and it will just swap the battery by the new one. But these concepts are not going to work on the private vehicle. This can be work on the commercial fleets, for example, 3-wheelers, or maybe on 2-wheelers. These are the famous coupler. These are the famous couplers. Typically used globally. China use the GB standards, America use SAE standards, and Japan also use the same. Let me just go. Yeah. So US and Japan use the SAE standards. Tesla makes sure that it has this kind of standard couplers on their vehicle, and they have their own superchargers and chargers, so they don't have to worry. For the European market, they have to make sure that they give IEC based couplers. For the Chinese market, they have to make sure that they have to give some other kind of GB or maybe other couplers. In India, we have a modified version of Chinese coupler, which is GB/T. Indian infrastructure, charging infrastructure is going to be similar like in the US. I'll explain you here. This is the last. Okay. For example, in India, they're going to be a AC charger and a DC charger, public chargers. They've already started deploying. Government has already shown a lot of initiatives. I think since 2016. In 2016, they have a program named as FAME, faster adoption of electric mobility and manufacturing of electric vehicles. Under that scheme, they have announced to invest 10,000 crores in the infrastructure and in the adaptability of EVs, also in providing the subsidies and in buying the electric vehicles to give it a push and for testing to their own government employees. I think it took 2 years. It was a 2 to 3 years of the span of time. They have invested 10,000 crores, and they have I think last year, 2019, they have announced FAME 2 program, in which they're again going to invest 10,000 crores in the same segment. But I think transition is going to take some more and more investments. But it's a good initiatives from the government. So this is a typical, I think, a DC charger where you have 2 slots. One is restricted to 100 volts, and the another will be restricted to 1,000 volts. 100 volts are for 2-wheelers and 3-wheelers, and for the vehicles who have 72 or 96 volt of batteries. There will be a protocol, there will be a communication protocol, there will be a handshaking. They have to make sure that the connector sits mechanically sits, and it is a proper connection between the charger and the vehicle, and then only the charging will initiate. For that, the BMS and the charger on the board has to provide the information to the EVSE, which is electric vehicle supply equipment, to the charger. Then you have a similar, I think this is the mobile application where you can pay based on the charge you are getting. One of the infrastructure is swappable. I think the owner of Reva, he sold Reva to Mahindra. Now he started a swappable business under the name of the company Sun Mobility. They are doing it in a very big way for the fleets, for three-wheelers mostly. So they are going to do a swappable structure. When you run out of charge, you're going to swap it to the charged one, and based on how much energy you are consuming, you have to pay, and it will be paid via your UPIs and other things. Okay, thank you very much. Any questions?
So yes, Abhinav, we have few couple of questions for you. And
Yeah.
meanwhile, those who have questions, you can start typing chat box. We will take it one by one. So the very first question is from Shashwat Samal. Why hydrogen fuel cell vehicles be efficient?
See, hydrogen fuel cell is again a proof of concept. There are some buses in India that are running on hydrogen fuel. The only limitation is the carrying. It's very dangerous to carry hydrogen fuel. The transportation is going to be a big challenge. It's like you are transporting a bomb. That are the criticalities, and that are the challenges for hydrogen fuel cell. It is a wonderful idea. I mean, if you are able to crack the this kind of bottleneck of transportation, then it's a good way to go. So there are proof of concept. There are many companies who have already working on the hydrogen fuels. There are some vehicles who come with the hydrogen fuel, but the only challenge is the transportation and storage of hydrogen fuel is very dangerous.
So again, a follow-up question from Shashwat again. So why Tesla is not coming up to India, and why there is no good infrastructure for the manufacturing of EVs?
Okay, so Tesla, just kidding. Tesla, obviously, when the initiation of fame happened before our Mr. Modi, our Prime Minister, he visited Tesla factory by himself. Our Chief Minister, I think, Minister of Transportation, Mr. Nitin Gadkari himself visited Tesla factory. They himself invited Mr. Elon Musk to put up a factory, at least an assembly line in India. But even Elon Musk has announced the same, that they're going to put up a manufacturing in India. But there are many challenges. There's a lot of doing business in India is not very easy as compared to the United States. It's not that easy. That is the reason why Elon Musk shifted from India to China. Now they have recently opened up a factory in China. I think in March.
Cool. So
Yeah.
yes, I suppose Shashwat you better answer. So coming up to the next question from Suman Pal. So how deep can a lithium iron phosphate battery be discharged?
100%. We are doing 100%.
Right.
See, every lithium-ion batteries, the specialty of lithium-ion batteries is that you can discharge it up to 100%. With the lead acid, now the lead acid are coming up with a deep cycle lead acid that can go up to 80-85%. Earlier, the lead acid won't be able to go beyond 60%. The specialty of lithium-ion batteries, it can go up to 100%, full to full. But with the NMC and other chemistries, mostly with the NMC, we don't go 100%. We try to discharge it up to 80% because we wanted to prolong the life of the battery. But with the lithium iron phosphate, the chemistry is very stable, so you can go up to 100% without much affecting the life cycle. So with the LFP, it can go up to 100%.
So coming up to the next, we have one question from Nishita Balyar Singh. So she's saying like store dot has a concept of a 5-minute charging battery for four-wheelers EV. So how feasible is that concept? Is it?
It's very feasible. I think we had a discussion just a few minutes back. Somebody was explaining about the superchargers and capacitors. So they have used a similar kind of concept. They try to combine the principle of superchargers with the batteries. And see, batteries are available where you can charge up to in full charge up to 10%. Sorry, in 10 minutes you can charge fully. But at the same time, you are losing something. With this, as I explained, lithium ion, the energy density is here. Supercharger, the energy density is here. They are combining all the technologies and they're coming up here. So you try to focus on something, you lose something. You cannot achieve all the trades. So I think what Store Dot is doing a wonderful job. And there are some Indian companies also. They are doing. Gigadyne is doing. It's an Andheri-based startup. They're doing a wonderful job. It's a proof of concept, but at the same time, the capacity of the battery which they are providing is much lesser than the lithium ion.
All right, all right. I hope, Nishida, you get your answer very well. Again, there is one more question from Pitambar Patra. Yes. So the question is there any disadvantage of speed charging regarding with battery durability?
Sorry, is there any disadvantage of?
Speed charging regards with battery durability.
That's correct. That's correct. So as I said, the power density and the charging rate is one of the factors that we should take care of. Mostly the lithium-ion stable chemistries, it is recommended not to go beyond 1C charge. Means at least it requires 1 hour to charge fully. I'm talking about NMC, in which we can get a decent amount of energy and volumetric densities. So of course, it is recommended not to go beyond 1C. If you go 1C, the batteries will charge, but the temperature is going to exceed, and it might, if you're not doing the cooling, and see, if you're able to control the temperatures while charging, then it's good. Like Tesla, they don't go beyond 1C. They are doing the superchargers, but they don't go beyond 1C. But during the charging, they turn on their cooling so that the battery temperature stays in the range.
I hope you get your answer, Mr. Patra. Right. So coming up to the next question by Mr. Abhishek. So in order for the batteries to start charging, what is the minimum volt and current requirement?
Obviously, for the lithium ion, for example, let's take an example of NMC. The nominal voltage of NMC is 3.7. The maximum voltage is 4.2. So you need a charger. If you are charging a single cell, you need at least 5 volt voltage, and the current is limited to the capacity of the cell. If the capacity of the cell is 3.2 Ah, then the current should not exceed 3 ampere. So I'm just taking an example. I'm just taking an example of a cell, so you can do the math and make it a pack and the battery. Yeah.
So I think there's a last question from Sashwat again. So why lipo batteries are not used for electric vehicles?
See, every chemistry, there are many lithium batteries. There are varieties of range of chemistries, but every chemistry has a different drawbacks. For example, the laptop batteries, you cannot use the similar laptop batteries in the electric vehicles because their life cycles are different. The requirements of the load is different. Lipo batteries, the load is different. The application is different. That's why. So it is recommended to use NMC for the electric vehicles. For some vehicles where the performance is not required, for example, electric three-wheeler, LFP is more recommended. And in case of buses, where the parameter of a bus is limited, so you can use LTO being a very expensive chemistry because they don't produce it at a bulk level, although the bill of material is plus or minus the same. In LTO plays a very good role in buses because they have a limited periphery, and in every stop they can charge, and they can charge it. You can charge it in the full 0 to full at the same level. LTO has other advantages. For example, the cyclic life. Normal NMC cyclic life is somewhere around not more than at the pack levels not more than 1500, but LTO can go up to 10,000 cycle life. Even and the buses, the space requirement, the space is available, so you can put more number of batteries. So I think LTO goes pretty well with the buses. I've actually seen one very good question. I forgot. Just let me just go through the chat. What is the average weight of the battery pack being used? It depends what range you want. There's no limitation. I mean, it depends on the cost also. For example, Mahindra ETO doesn't. Sorry, Mahindra e-Verito does not go beyond 20 kilowatt hour, whereas Tesla is using, in a similar kind of space, they are using 100 kilowatt hour because of the cost of the batteries and the range. So it depends on what you want at the output. One more questions. Think what about the maintenance of the Tesla? Yeah. Okay. So very good reason to adopt electric vehicle is because they are maintenance free. The only good thing is the software. Tesla, they don't consider themselves as a automobile company. They consider themselves, they say they are a tech company. So they have the abilities to maintain or to operate your vehicle remotely, even in some crises, in some of the disaster crises, in cyclone or some other. We have heard news that they were able to extend the range of the vehicle by choosing the window of the operation remotely. I mean, you just need to call them or you just need to request them so they can open the window so that you can have the extra miles to travel and reach to your home. In case of crisis, we have heard about it. Maintenance, the good part about the maintenance, the IC-based engine, the companies, they don't want to go towards they don't want to produce electric vehicles. The reason, the reason are in the in the in the IC-based engine, the moving parts are somewhere around in the range of 10,000, approximately 10,000 moving parts. More moving parts requires more number of maintenance, and their annual turnover comes from the spare parts after sales. They don't make enough money by selling the vehicle, but they make a good amount of money by selling the spares. That's why if they are going to go electric, the maintenance cost is going to reduce by negligible, because the moving parts of the electric vehicle is not more than 100, and electric vehicle is maintenance free. We haven't seen any such kind of issues. If you are able to, if you are delivering a good product like Tesla, and maybe in coming time we might see some of the issues. So you just go through the showroom and services. The maintenance is very cheap, I would say. So the operational cost of the electric vehicle and the maintenance makes it a cost viable and feasible vehicle commercially.
Coming up to the last question for the day. So there's
Yeah.
a question from Niharika Paul. Battery container should be acid resistance. Therefore, it is made up of which material?
So these are acid-free batteries. Acids are being used in the lead acid battery. So there are maintenance issues in the lead acid that you have to make sure that you fill the water timely. And these are maintenance free. There is no acid inside the cell and nothing. So there's no leakage. There's no possibilities or chances of any leakage or anything else. These are very safe batteries.
Thanks, Abhinav, for complying with our request and showing up. And it was extremely informative. I'm sure a lot of people enjoyed the session.
Thank you, Dilip, for having me. Thank you, everyone. Stay safe, stay healthy.